Exam 1 will cover chapters 1, 2, and 3. Outline here shows that there's going to be 5 problems on the test. Problem number 1 will be classifying differential equations. So you have a differential equation. You have to answer questions like, is it first order, second order, or whatever? Is it linear or nonlinear? Is it homogeneous, Bernoulli? Is there a substitution you can use for it? Is it exact? Those kinds of questions. Problem number 2 is to verify a solution for a differential equation. If you have a differential equation, you don't have to solve for it because there's going to be a solution or maybe 2 solutions, and then you're to verify which one or both might be solutions to the differential equation. Yeah? Yes. Yep. And then that's for problem number 2. And then the solution that I'll give you will probably be a general solution. And then if I give you initial conditions or boundary conditions, then you should be able to solve for the particular solution. That's problem number 2. Problem number 3 would be modeling with differential equations. So we've taken a look at a few models in class, and you had more models that you had to do in homework. So the models in class dealt with growth and decay, and we also had the temperature, Newton's law of cooling, and we also did an example with circuits. So the idea is that with words, you should be able to come up with a differential equation, and if it's a first order differential equation and it falls under one of the categories that's covered in chapter 2, you should be able to solve for that differential equation as well. Problem number 4 will be a couple of differential equations where you're going to be solving for it with initial conditions. And problem number 5 would be some special differential equations where you have to use some sort of substitution to be able to solve for it, either Bernoulli or one of those other substitutions that we've done in class or you've done in homework. Okay? So that's the test. Any questions? There's a review sheet here. We can take a look at it. So you're going to be allowed 1 page of notes, and just to make everything all even, back front. I know there's people who have 89 or even Inspire calculators that are almost work like computers and can find differential equations and stuff, so we won't have calculators for the test. So you should be able to integrate, and I'll leave up to you what you want to put in that sheet of notes. If you want to put a whole bunch of integral from table of integrals, or some quick formulas on integration by parts or partial fractions or stuff like that, then that's what you can put on there. Anything else? All right, let's take a look at the review sheet. The review sheet is here that you can click on and download. So our test will not be multiple choice. So as you're looking through this review sheet, you can pretend that there's no choices, or you can pretend that when I ask you these questions, you can try to figure out more than what they have here. So this was my plan, was to go over this this practice test. And you guys have any other questions about other stuff, like homework or anything? Yeah. Okay, I can have office hours Monday between 10 and 11 at the STEM Center. That's the morning, right? All right, let's go through this. If we see a question where we can extend the question to more questions, and we'll do that. So problem number 1, the differential equation y double prime plus 2y prime plus 3y is equal to 0 is it, what order is it? It's second order, so we got two choices. Is it linear or nonlinear? It's linear, so your choice is second order linear. Okay? Can you give me an example of a second order nonlinear differential equation? So same thing. So if you just do something to one of the y's, any of the y's, it could be the y prime, or even the double prime. If you do something to that, take it to a power, or take it to a trig function, or whatever, then it's going to be nonlinear. Yeah? Yeah, if 1 over y is also nonlinear. Okay? Can we solve for this? Do we have any techniques to be able to solve for this? So this is going to be a topic that's covered in a later chapter where we can solve for second order linear differential equations. Let's make up another problem out of this. Is this a solution to the differential equation? What would you do? So take first and second derivative of the equation and then plug it in. So plug it into the original differential equation. So, what is it, 18? Then 22? 18? So, the point is that if this was a solution to the differential equation, we should have this thing to equal each other, and they're not. So this is not a solution. Okay? Any questions? All right. Let's go to next problem. Okay, what order is this one? First order. Is this linear or nonlinear? So the x is in sign, but we don't care about the x. X can be anything we want, or anything anyone wants, as long as the y is linear. That's what we're shooting for. Can we solve for this? So this is a first order linear differential equation, and the first thing we should ask for is an integrating factor. Do we need an integrating factor? So let's solve for this. And we start off with looking for an integrating factor. If it's a first order linear differential equation, it's written like this already, and the coefficient of y doesn't have to be constant. The coefficient of y would be your p of x. And so your integrating factor is e to the integral of p of x dx. So what's your integrating factor? E to the 3x. And so if you multiply this by e to the 3x, you're going to get e to the 3x times y prime plus 3e to the 3x times y. We know that that left-hand side is going to be the derivative of a product, and the product is going to be the integrating factor times y. Right? And then the other side is e to the 3x sine x. What? You guys don't want to do double by parts on the test? Yeah. So there is a formula for this. If you guys have the table of formulas, that I don't know if you want to write all that. No. So I'll try to remember to not have something this difficult on the test in terms of integrals. It's taking a while here. Hmm? Oh, what if we just put actual numbers? So when you solve for this, when you integrate both sides, you'll come up with something like this, and then you still need to divide out by 3 e to the 3x. So you got y is equal to, if you divide out by e to the 3x, the e to the 3x looks like it'll just cancel. 1/10 cosine x minus 3 sine x, and then that's it. Oh, it's right here. So this is a general solution. Oh, yeah. So divided by e to the 3x. Okay? So this would be a general solution if there's no initial condition, so we could be done here. Any questions? I hope this step is comfortable going from your integrating factor to this, because we've done it a lot already. I'm hoping that you've done it a lot because you guys had a lot of homework, and this was a quiz problem, and almost everybody got a 10 on the quiz, right? So whether you copied it from somebody else or you did it on your own, the fact that you did it should mean that you know how to do this, right? It depends. If it's an initial value problem, so problem number 4 on the test, we'll have a couple of initial value problems with initial conditions, so you'd have to solve for C. And then the last page on the test are just solving for the general function, so general solution. So that one you don't have to solve for C. Okay. Let's go check another problem. Try this one. The values of m for which y is equal to x to the m is a solution for this are, select the following. So what kind of differential equation is this that makes us think that we can solve for this? Is it linear? Right, so x squared doesn't matter. So in y, which is what we're supposed to look at, this is a linear differential equation. So it's a second order linear differential equation. So any other hints on how to give this a shot, how to do this? Divide by x or x squared? So we got y double prime minus 5 over x times y prime plus 8 over x squared is equal to 0. Does that help us any? Y is equal to what? Yeah, so this is saying that this is some sort of solution. Now, we don't have the perfect solution because we don't know what m is equal to, but they're saying that this is a solution to the differential equation. So if that is in fact the case, we should be able to take that x to the m, we should be able to take two derivatives of that, right? Which shouldn't be a problem. And then plug it into here to see if we can get it to force it to equal to 0. So let's do that. Let's take a couple of derivatives here. Y prime is, what's the derivative of x to the m? And then the second derivative? What? Okay, so this is my second derivative, and it looks like if I just put that in there, I should be good to go, right? Got it. So x squared times, and y double prime is going to be m minus 1, x to the m minus 2, minus 5x, and the first derivative is m x to the m minus 1, plus 8, and then the original function is just x to the m. Is that good so far? So now let's see. I can combine some x's here. What happens when you multiply two things with the same base? Add the powers, and so what's the power going to be? And then same business over here. What's the power going to be? X to the m. And then the last one already has power x to the m. So, any suggestions on what to do? So I'd factor that out. Then I have, let's call this m squared minus m minus 5m plus 8 is equal to 0. So x to the m is your independent variable, and if that's equal to 0, then you have your solution is y is equal to 0. What kind of solution was that again? Trivial. It's a trivial solution because for differential equations in standard form that's equal to 0, 0 is always a trivial solution. So we're going to assume it's not a trivial solution, which means we're going to see when this factor is equal to 0. Yeah?
So you're saying there's no value for n equals 0.
There's no value for x. We don't want x to be 0. Because if x is equal to 0, then y is equal to 0, and that's a trivial solution. So what we want is we want to know when this thing in parentheses will be equal to 0, and that's hopefully one of these choices.
I remember going over trivial solutions in algebra, so I don't remember.
With the what? A trivial solution is just y is equal to 0. And when your differential equation is equal to, something's equal to 0 in your differential equation, then 0 will always be a solution. But we want to know if there's more solutions beyond that. And what are the solutions here? Positive? All right, so it looks like these two would be your solutions. Questions? X to the m? Then it would be a 0, the trivial solution. Y is equal to 0 is a trivial solution. Okay, questions? All right. Let's check for another problem. Want to do 5 or 6? 5 because it's a word problem?
You could just do this. You could just completely exclude all of 1.4 or whatever section this was, and then you won't have to ever teach it. Would you do that?
Okay. All right. Population of town increases at a rate proportional to its population. Its initial population is 1,000. Correct initial value problem for the population is given by this function. So this is a translation part. So if you were to have this on your test, or when you run into this problem on the test, just read through it and translate word for word. The population of a town increases at a rate. This would be dp dt. It's proportional to its population, period. Proportional to its population. So K times P, the population. So proportional is equal to K times, and then to what? Its population. The population is P. So that's it. That's your differential equation. Okay? So if you were to have something like this on the test, it'll hopefully be about as straightforward as this, where something, some rate increases proportional to something else, and that something else, you just have to find an expression for that something else to make your differential equation. The initial population is 1,000, so population at 0, that's usually the initial, is 1,000. And so that's the first choice. So what would the words be if this was your answer? Also, so proportional So if it's proportional to the square of the population, you just take your population, you square it. How would this go in words? It is proportional to what? It's what? Maybe. It's proportional to the population. Population times, is it times? Proportional to so we could think of sometimes we can think of 1 as like 100%, although you wouldn't consider this. Yeah, so the setup for here has to be a little bit more complicated because it'll have to be more. It'll have to explain what 1 minus the population is. So we can say the percentage P equals percent of the population. That's what? I don't know. Yeah, this would be one of those epidemic differential equations. So out of all the population, the P would be the ones that are infected, and then 1 minus P would be the ones that are not infected, right? So P, population, infected. Maybe they're zombies, right? 1 minus P, population, not infected. Okay, so maybe it could look like this. But you can look at the words and see how they relate to the differential equation, and that's what you need to do. That's the connection that you need to make. Okay, questions? All right, this thing you could solve for, right? It's going to be some exponential function. All right, let's move on. I was going to skip number 6. All right, 7 or 8. Okay, so let's not do 8 then. Solution to the initial value problem is that where C. So this is a case where you would be given the general solution and you'd have to find a particular solution just by solving for C. I suppose we can assume that this is in fact a solution. We don't have to test it. So I'm not going to test it anymore. But we do know that this is your initial condition, and so with the initial condition we should be able to find C. So y of 1 is equal to, let's put 1 in for x, these are the x's that were replaced. And this is supposed to be equal to, according to this initial condition, equal to 1/4. So combine this, bring it over to the other side. So we can write it as 1 over e squared or e to the negative 2, and which is a constant because there's no more x's. So that's your C. Is that, it's one of the choices. All right. And if you want to do more of an exercise, you can check to make sure that this is a solution for this differential equation. Take the derivative once and then plug in all the values and see if you get the right answer with the C. So even with a C there, you should still be able to get the correct answer. All right. All right, let's move on. Now this is the temperature of the coffee, so I don't know. I deleted some problems. Maybe I should have deleted that one too. All right, this is the same one. Let's take a look at 12. Autonomous differential equation. So automatically think of x as your independent variable, but in this case t is the independent variable and x is your function. So this should be x of t, your solution. So this is an autonomous differential equation because if you set the derivative equal to all the other things, all the other things are only a function of x. There's no t's in there. And because it's an autonomous differential equation, we should be able to figure out where we have, what do you call those things? Attractors and repellers. The points that are stable and unstable. So let's approach this by looking at the face portrait. That's what it's called, right? Face portrait. And they kind of made it easy for us because now it's a third order polynomial, third degree polynomial, but it's already in factored form, so that makes it nice for us to identify our zeros. So when you set this equal to 0, x is equal to 0, x is equal to 1, x is equal to negative 1, those are going to be our solutions. But now we have to check where things are increasing and decreasing, and it kind of reminds me of the first derivative test in calculus. So if we put a number that's, let's start from the bottom, put a number that's very negative, this is a negative, this is a negative, and this will end up being negative, right? So negative, negative, and a negative is negative. More negative. So that's going to be going away from 1. Now if we put a number between negative 1 and 0, it's still going to be a negative, but negative 1 minus 1, so that's still going to be negative, right? So this is negative, and then now this should be positive because 1 is bigger. So it looks like negative 1 is an unstable equilibrium. Between 0 and 1, now we're starting to look at the positive values. This would be a negative and a positive, so this is going to be decreasing. So 0 is a stable point, and then positive, 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 So let's identify that 0 is stable and positive and negative 1 are unstable. So increasing between 0, increasing everywhere and decreasing everywhere are not correct. Is it correct? D is correct. So increasing between 0 and 1, between 0 and 1, it looks like it's supposed to be decreasing, so that's not right. Decreasing if x is between negative 1 and 0, that's also not correct, is it? Increasing if x is bigger than 1, so this is the only one that looks like it's correct. You don't need to do this, but if you were to draw a slope field, I don't know exactly how the slope fields are going to look like, but we can kind of guess. That it's going to be decreasing here, increasing here. And etc. Yeah, that looks okay. All right. So if you had a point, so what can you tell me about if I had an initial condition here that says x of, should we put it, x of 1 is equal to 1/2. What can you tell me about this graph? It has a negative slope. It's always going to be decreasing. So solution will be decreasing. You guys agreed to that? You guys understand why that's true? And then it would be what? Approaching 0. Y? There's no y's here. There's no x's here, or there's no y's here. Right? So this is your t-axis, this is your x-axis, this is your x-axis. Right? Did you guys get that the x here is not the independent variable, right? So if we're following and finding out information about an initial condition, when t is equal to 1, x is 1/2. When t is equal to 1, x is 1/2. That would be somewhere over here. Right? And so you're stuck within this interval or within this range. And this is about all you can say about it, that it's decreasing and it's going to be approaching 0. Okay? All right. Yeah? If the arrows are going towards that point, then it's stable. If the arrows are going away from that point, they would be unstable. So the arrows, we figured out the arrows by putting in values that are between these points. Yeah, so if it's stable, it's an attractor, and if it's unstable, it's a repeller.
Do you have to like use like paired form for saying that?
No,
Say X or usually Y.
because x is the whole value of it's a line.
Oh yeah.
Okay? Any questions? All right. Yeah, these end up being asymptotes. So whether they're asymptotes for going positive or going negative, they're asymptotes of all your solutions. All right, let's move on. Do we want to do an integrating factor? Or this one? Exact solution. Let's do an exact solution. So let's check. One of the options is it may be that this is not exact. So maybe we should check if this is not exact first before we go through the process of trying to solve for this as if it was an exact equation, because if it's not exact, then we're just spinning our wheels. And so this is a differential, and we want to treat each of these sub-functions as if they were their own functions of x and y. And then if we can get m, the derivative, the partial derivative of that with respect to y, and we take our second function, n, we take the partial derivative of that with respect to x. If they happen to be equal to each other, then they'll be exact. So holding x constant for that first one, the derivative of 2xy is going to be 2y. And the derivative of this thing with respect to x, 2x. So they're not exact. What's the derivative of this with respect to y? 2x. Who said 2y? Somebody said 2y. So derivative of m with respect to y is the variable, 2x is a constant, so that's just 2x. So yes, this is exact. How do you solve for exact equations again? Use some integrals. Okay, so m, we have to pretend that m came from a function came from a function where you had taken the derivative of that original function with respect to x. And so 2xy is your m, and to try to recover our original function f, we need to take the integral of that with respect to x. So integrate 2xy with respect to x and x squared y. Plus some function. It could be a function of y. As long as there's no x's in there, this was treated as a constant. So there's a possibility that there's a y in there. So you take your n function and do the same thing, assuming that this is derivative of some function with respect to y. We take the antiderivative to try to recover your original function with respect to y. And so this is x squared y plus y. plus some other function that could possibly have an x in it. So from here we can kind of deduce that your original function is x squared y plus y, and then some other constant. Now this is a real constant with no x's or y's, but just a regular constant c. So what is the solution? A? This isn't a solution now. So is your answer A? B? What's the difference between A and B? It's the same thing? So you put the plus C on the other side, it would be the same thing? Yes. So what's going on here again? So which one's the correct answer? So it'd be one of those things where I can either choose A or B as my correct answer and everything would be fine. What? You could think about it that way. Remember, for exact equations, that we're assuming that your solution comes from f of x, y equals 0. What you're assuming, just if you let's try to remember that whole discussion with exact equations. That whole discussion with exact equations kind of began with z is equal to f of xy, and then you take the differential of that, and you get the partial of f. Let me write it like this instead. So f with respect to x times dx plus f with respect to y times dy. And if that whole thing was set equal to 0, then we can assume that this is either set equal to a constant or set equal to 0. It doesn't matter because that constant can live with the f or can be separated from the f. But if you have a function of x and y combined equal to 0 like this, and then you came up with this differential equation, in order to go backwards to get your solution, we want this to be equal to a constant or equal to 0. And the point is that now this is, remember, in a differential equation, we're looking for a function. All right, we're solving for a function. And if we're solving for a function, we need to know what that function is, and we need to know what the independent variables are. So we're solving for a function y, and in this case, y is just kind of integrated and intertwined with x. And so our solution here would be an implicit solution. And if for some way we can solve for y, then we can get y explicitly. So if you write your solution to a differential equation looking like this is clearly not an equation, it's not a function, and if I were to try to solve for y, I wouldn't be able to because there's no equal sign. Now this one, it looks like we can actually solve for y, so if we take y out and solve for that, y is going to equal to c divided by 1 plus x squared. And now we have a solution that looks like it makes sense to us if we were to write it like this. It's a solution to a differential equation. Okay? So your solutions to differential equations should either look like y equals to something or something with a y in it, but it has to be an equation. Because then you can say that you have an implicit solution to your differential equation. Does that make sense? I don't know if that made sense. According to your faces, no, it doesn't make sense. Bottom line, equal sign, good. No equal sign, bad. A would be wrong in this case. So the correct answer is B. Well, you won't have a multiple choice on the test, so then it would be wrong. How many points would I take off? I'd probably just take off 1 point, maybe 2. Yeah, because it needs to equal to 0 business. No, it'd still be wrong. Okay. Exact equations. I have time for one more. 16 or 17? 17. So the differential equation has a solution, and then we have to select the correct solution. So this is one of those where a substitution might be a good idea. And the substitution, remember, I think we went over 3 types of substitution. One is the Bernoulli equation, where you let y equal u times v or something like that. And then there's another substitution if it's a homogeneous. No, that's the one for the homogeneous. Oh, I'm getting mixed up now. All right, don't get mixed up. I can't. I'm just going to tell you that this particular substitution is if you have x, oh, there's no z here. Getting carried away with Calc 3. But if you have an expression that has an ax plus by plus c, you can replace that with u and then change your differential equation to something with a u in it. So that's what we're going to do. We're going to let u equal to 4x plus 2y plus 3. So this is just essentially u squared. And then we're going to find a differential. Du is equal to, now with respect to x, we'll just say 4x dx, 4 dx over x, or whatever, plus 2 dy dx, this is a y, and then the 3 is gone. So you can replace your dy dx with whatever this is equal to. So dy dx is going to equal to 1/2 du minus 4 is equal to And you got to replace everything else so that it's in terms of we're totally getting rid of the y variable, and we want everything in terms of u, so that's just u squared. Oh, this is du dx. So now you have u prime instead of y prime, and everything else, there's no more y's in there. Everything else is in terms of u, and this would be a separable. In fact, this is this is a separable differential equation that we should be able to solve for. So let's see. I think we can multiply both sides by 2. So this is u prime minus 4 is equal to 2u squared, and u prime is equal to 2u squared plus 4, and you can finish this, right? With respect to x, sorry, this is with respect to x.
2 times the y carried with the 2 times. Oh, okay.
So this is a separable differential equation. It's already separated. You might need to use some trig substitution with a tangent in it. I don't know. I have a minute left. Maybe I'll start packing. That's what you guys do, right? There's a minute left to start packing. All right, we're done. Good luck on your test on Tuesday. Oh, this thing has solutions at the end, right? If you look at the end, it's multiple choice, so it has the answers in the back.